Earthquakes occur whenever pressure builds beneath Earth's surface and is suddenly released, causing large blocks of the crust to move. This release of stress is what creates the shaking we feel during an earthquake. When Alfred Wegener first proposed the idea of continental drift, his ideas were rejected for more than 50 years. The main reason was that he couldn't explain a mechanism powerful enough to move entire continents. It wasn't until scientists began studying seismographs from around the world and how different seismic waves travel through solids and liquids that they were able to theorize the internal structure of the Earth. Powerful earthquakes, especially those with a moment magnitude of 5.5 or higher, can be detected by seismograph stations around the world. Scientists noticed something interesting. P waves, or compressional waves, traveled all the way through the Earth and were detected on the opposite side of the planet. S waves, which move in an oscillating motion, were only detected at closer stations. Because S waves cannot travel through liquids, scientists concluded that Earth must have a liquid outer core. This discovery was a major breakthrough in understanding Earth's interior and helped explain how plate tectonics actually work. Most earthquakes occur along plate boundaries, especially around the circum-Pacific belt, which we know as the Ring of Fire, where the Pacific plate is subducting beneath all of its neighboring plates. Earthquakes in Europe and Asia are largely because of the African, Arabian, and Indian plates colliding with the Eurasian plate. That said, earthquakes don't only happen at plate boundaries. As continents bend, twist, and compress under pressure, stress can build in the middle of the plates as well, causing intraplate earthquakes. Nearly 2,000 years ago, Zhang Heng developed a method for detecting earthquakes in China. Modern seismographs that record the size and direction of vibrations were later developed by British geologists studying earthquakes in Japan. Scientists also realized that they could triangulate earthquake epicenters by comparing data from at least three different seismograph stations. In 1975, an earthquake was recorded on seismographs in Fargo, then detected at Minneapolis, St. Paul, and finally picked up in Sioux Falls. The earthquake had a moment magnitude of 4.6, which was strong enough to be felt by the residents in Morris, Minnesota, which was the epicenter, and nearby towns, but also was a great example of how earthquakes can be detected far from their epicenter. This is especially useful when trying to triangulate an earthquake epicenter in remote or unpopulated areas. The modified Mercalli Intensity Scale is a useful way for non-scientists to estimate how strong an earthquake feels. The intensity of 5 is strong enough to wake people out of their sleep, while the intensity of a 4 might cause furniture to move. I experienced this firsthand in Naples, Italy in 2008, almost 20 years ago. I noticed my bed on the fourth floor of my hotel room gently swaying. It was barely noticeable, and most people on the trip didn't feel it at all. That likely would have been an intensity of 2 or 3 on this scale. When I later checked seismic records, Naples, Italy experiences roughly 15 magnitude 2 to 3 earthquakes every week, meaning that what I felt was considered normal background seismic activity for that area. Growing up in the 1980s, I remember hearing about earthquakes measured on the Richter scale. The Richter scale measures how much the ground shakes, not how much it feels. The magnitude 5 earthquake shakes the ground 10 times more than a magnitude 4 earthquake. It also measures energy released. So a magnitude 5 earthquake would release 32 times more energy than a magnitude 4 earthquake. Today, scientists use the moment magnitude scale, which measures how much movement occurs along a fault line and how much energy was released. It's the most accurate scale, but it's also the least accessible for non scientists to estimate when trying to figure out how strong an earthquake was. The Morris earthquake of 1975 was 4.6 moment magnitude. While it wasn't strong enough to send seismic waves through the entire planet, it was easily detected by seismographs in Fargo, Minneapolis, St. Paul, and Sioux Falls. The shaking and minor damage aligned well with what we'd expect on the modified Mercalli Intensity Scale for a 4.6. Even so, the 4.6 earthquake that Morris experienced in 1975 released enough energy to be equivalent to 1.8 million kilograms of explosives. One of the biggest earthquake threats today isn't the shaking itself, it's tsunamis. About 20 years ago, an offshore earthquake near Indonesia triggered a tsunami with waves over 100 feet tall. That's about the height of a 10-story building. Living in southwest Minnesota, we don't even have 10-story buildings. Over 200,000 people were killed. This is largely because Indonesia is densely populated and much of the land is low lying, so a 100-foot wave can travel further inland. About a year after I visited my sister-in-law in Japan, an offshore earthquake triggered another devastating tsunami. While her family lived safely in the mountains, the coastal areas of the Fukushima prefecture were hit hard enough to cause a nuclear power plant meltdown. Japan is one of the most earthquake prepared countries on Earth, yet nearly 20,000 people were lost. When I visited Japan, I felt tall buildings swaying during frequent magnitude 2 to 3 earthquakes. Events like that are so common that they're barely noticed due to the advanced building design. Earthquakes are simply the shaking of the earth, but even moderate earthquakes can be deadly in areas with poorly constructed buildings. In Haiti, many homes were made of mud and weak materials in such a way that the 2010 magnitude 7.3 earthquake caused buildings to collapse while the shaking ground behaved almost like a liquid in a process known as liquefaction. There are many other courses and lecture series available that explore earthquake hazards in greater depth, including earthquake safety, tracking, and damage prevention. Moving on to rock deformation. Over time, Earth's constant pressure and release reshapes the landscape. When rocks are compressed, they form anticlines and synclines, which creates crest and trough looking structures in the layered rock. We often don't see these structures until erosion or drilling exposes the tilted sedimentary layers. In places like the Black Hills, magma rose beneath the surface but never formed into a volcano. Over tens of millions of years, the rock cooled, solidified, and was exposed to the elements, resulting in igneous and metamorphic rocks in places like Mount Rushmore and Hardy Peak. While the younger sedimentary rocks like limestone and sandstone form caves on the outskirts of the hills, like Jewel Cave and Wind Cave. Normal faults occur when gravity pulls the hanging wall of a fault line downward. Reverse faults happen when compression forces the hanging wall upward. When multiple fault blocks form, we get fault block mountains, such as the Sierra Nevada. Subduction zones create volcanic island arcs, which we talked about in the plate tectonics lecture. Oceanic continental subduction zones form mountain ranges like the Andes Mountains. However, when microcontinents get in between oceanic continental subduction zones, we get mountain ranges that are called cordilleras, and those are like the Rocky Mountains. Finally, we have the continental-continental collisions that we also talked about in the plate tectonics lecture. This creates massive mountain ranges like the Himalayas, but other mountain ranges that are formed in this manner are the Alps, where the African plate is colliding with the Eurasian plate, and also the Appalachian Mountains. The Appalachian Mountains were formed long ago, prior to Pangea, when the North American plate was colliding with the African plate, before eventually separating about 200 million years ago. That's all I've got for you today. Thank you so much for listening, and I'll see you next time.